agenda. So next we have an invited talk, a keynote talk given by Bean Kim. Bean Kim is senior research scientist at Google Brain. She's working on building interpretability methods for already trained models or building inherently interpretable models. She gave already a great talk 2 years ago in our workshop, so we are very happy to see her here again today, giving a talk about interpretability with skeptical and user-centric mind. So Bean, the stage is yours.
Thank you. Thanks for inviting me. I had so much fun last 2 years ago and really happy to be back. And having done an organizing multi-year workshop, I know how much work it goes into, and it requires a lot of passion and time to organize something over and over again. So kudos to the organizers pushing on this very important topic. So I'm curious for the audience if you've ever been asked any of the following questions by your friends, by your family members, or by your colleagues who work on different topic. They might ask, so what do you really mean by safe? Safe in automated driving? Or do you have the metric? Do you have the mathematical definition? What do you mean by safe? And you have been asked any of these questions, I feel you. I get the same questions too. If you replace safe or safety to interpretability or interpretable, it's exactly the set of questions that I get. Sometimes it goes a little beyond that. Beyond that, and I was asked actually a couple of days ago by somebody, what do I think about killer robots, or what do I think about singularity when human machines exceed humans' intelligence? So what do we do when this typically happens? I typically ask, okay, well, do you have some time? I can explain. And I start explaining why it's such a complex problem. And it is not really as easy as having a one definition or one metric. Then we talk about how human psychology has been trying to study similar topics for centuries in sort of global sense. And I point out that also many real world problems are do not have any mathematical definition. And if you take it as even simple as building a classifier, say even image classification, we don't quite agree what the best metric is. And even before considering fairness and that complex issues, just think about what is it the optimal metric for building a classifier that best serves the user? It's pretty difficult. How do you define that? Well, we really only have a proxy for them because real world problems are complex and interpretability or safe automated driving is not alone. And I really enjoy this type of conversations when we both have time to sit down and have that conversation, and it often turns into quickly philosophical, meaningful, and complex. And we are doing our best to invent methods to help us to be safe or interpretable. We both walk away feeling that maybe we had learned something from each other. That all sounds good. It's true that we're all trying to make safeguarding methods or interpretability methods, and we thrive to make better methods every day. But I'm here to ask an annoying question. I'm asking, is that enough? And the answer, another annoying answer that I'm about to present is that I don't think it's enough. I don't think good intentions are enough. And specifically, I don't think focusing on making a new way to be safe or interpretable is enough. It's important to develop new methods. I do it too, and I will continue to do it. But I think the problem that we're studying are so complex and so difficult. We have to try to go beyond that, and we have to think critically about what we are doing in every single step in the way. So in this talk, I'll talk about main three things where I argue that what we're doing may not be enough and suggest first steps towards each item. So first of all, just making a new method is not enough. We've made a lot of methods, and maybe too many, each of which gives different explanation for the same model. And more recently, there has been a family of work from skeptics who've shown that explanation might not be showing what you think it's showing. And I will present a few series of work in this flavor that we did over the few years. Second, we made a lot of methods, mostly thinking about us, machine learning experts, who breathe and live in machine learning. But machine learning is a powerful tool, and it shouldn't be just accessible to machine learning experts like ourselves, a particularly privileged population, in my opinion. So I argue that we have to start actively think about equitable usage of this technology. And we propose a method that can provide explanation in the language of a user, regardless of their machine learning expertise. And third, I argue that one progress is not enough. When we write a paper, we have done some good work, but we still know that there are lots of things that can be improved, which we put in future work, and as if we were actually going to work on them. But really, we want maybe somebody else to work on them. At least I was like that. Here, I wanted to show you where I followed a line of work with a lot of smart people, and on a basic idea that was conceived 3 years ago. And we improved that work over and over again whenever we stopped asking, okay, how can we do better? What are the downsides of what we have, and how can we improve that upon? So let's jump right in. Developing method is not enough. We need testing. Without testing, giving an untested, a questionable explanation, I believe, is worse than not giving an explanation at all. This work, it starts with a sanity check for saliency maps, which you might have heard of. I'm going to cover that briefly before sharing follow-up user studies that we did. So focus of the testing today is the post-hoc interpretability methods. And many of folks in the audience would know what this means. You have a model, somebody gave it to you, you can't change it. And the question is, can you give me the evidence of prediction? For example, why was this image predicted as a junco bird? Popular method, as many of you are already aware, saliency maps that leverages this elegant idea of derivative of the logic layer with respect to every single pixel. And this measures the sensitivity of each pixel. If it's more sensitive, it's more important. And thanks to this elegance of simplicity, there has been explosion of methods in saliency maps, including my own work in 18. And here's some different methods. It kind of makes sense. The popular method 1 and 2 shows the boundary of the birds. Maybe this work shows more the whole body of the bird. Sure. But taking a step back, we asked this question about, okay, so you said this is evidence of prediction. So which means this function you built takes a prediction as a variable. So that means that if I change the input to this function, the variable, the prediction, output should change, the explanation should change. And in extreme case, if the prediction is random, then the output should really change. Because if it doesn't, it may indicate that that variable, this function isn't the function of this variable prediction. So we tested this. We got a network that predicts what's in the image pretty well, superhuman performance, in fact. We randomized them, and we got the explanation for many, many images. And we learned that, well, it doesn't actually change very much for this randomly predicting model. In fact, 3 out of these 6 pictures that I just showed you a couple slides ago, 3 of them are generated from random network. And I challenge you to guess which one of them might be. So 3, probably one of these 2, one of these 2 of my work, and one of these 2. And the answer is number 2, this one, that one, and popular method number 4. Those are generated from random network. And I don't know about you, but I personally can't tell. I've been staring at this picture for years. I still can't tell. So we did this for many, many popular methods, and we show that some of these methods actually don't change their appearance at all. And we did a number of quantitative ranking methods to use ranking methods or image similarity metrics to confirm that finding too. Just for a second. So since this work came out, it has become one of the go-to tests for pixel-based interpretability methods. I've seen reviewers asking for running these tests. Some papers come with these tests. And since then, there has been a number of great work that keeps this healthy, skeptical point of view of what we're doing. Recent work on calling gradient themselves in question. And these are very important line of work that we need to continue to do good science and keeping it critical. So that one was great. We worked on that and we thought we were successful in calling attention to the importance of being critical. But there's always this lingering question in our minds, because the confusing thing is that these methods have shown to be useful for some downstream tasks. And some papers showed and worked with doctors to show that these methods help doctors to be more efficient, which is great. So maybe there are some real tasks that these methods are in fact helpful. So what are those? So in this work in 2020, we try to answer this question by brainstorming ways of a typical bugs that a machine learning engineer may encounter in the course of developing and deploying machine learning. So for example, in training data, engineer may have labeling errors or spurious correlation. In the test time, they might have auto distribution problems. So what we did is we hired a lot of subjects and we asked them, okay, imagine you work in a startup, you're going to sell animal classification model. And here are the images, the individual images, here's the prediction, and here's the attribution maps, the saliency maps, the explanation. And we asked, would you recommend this model? Would you sell this? And why? Was it because wrong or right label or the prediction or the explanation? So note that we gave them the prediction here, and we debated this for a while, because if we give them prediction, then we cannot tease apart how much they relied on the explanation versus prediction. They might just look at the prediction and made a decision. We decided to provide this to the users because it's just unrealistic not. If you're an engineer, you have a model and you have explanation, chances are that you also have the prediction. So here's a few samples of the results. We asked, can these models help us find out whether the model, the new test data is out of distribution? And it turns out that yes, maybe subjects are very uncertain about these models that are put out of their distribution. And some because of the wrong label, but some because of the unexpected. Oh, I'm sorry. I was jumping ahead of time. So this conclusion of this study is actually it probably cannot tell us about other distribution. And a lot of folks said it was because of the wrong label. But the problem really we find was that they thought explanation was presented as expected. And this is one of the cases where by giving explanation, we are building false trust when the user shouldn't have that trust. So here is another type of bug. Let's consider spurious correlation. Now here I'm showing you a model and two different inputs with the bird and without the bird. And I want you to guess whether we are classifying the background or the bird. So was the bird spurious correlation or was the background spurious correlation? The answer is the bird was the spurious correlation. So we were classifying the background and we constructed this data set so that bird is highly correlated with this particular background, the ocean. And the results from this experiment was what I was confused with. It was more encouraging. Maybe a lot of users thought, yeah, the explanation is a little bit weird, and that's why I'm a little uncertain. So that was encouraging. So so we thought, okay, maybe the detecting spurious correlation is a promised direction. Maybe this is something that these methods can do. So in our ongoing work, we're digging deeper into this question. Can we capture all types of spurious correlation? What about other methods like concept-based methods or example-based explanation methods? So we test with 3 different kinds of spurious correlation. One like tags, like MGH is a hospital in Boston, or this stripes that got randomly inserted in the image. We did that. Or Gaussian blow, which is a little more visually less obvious case. And we're curious, okay, how far can we push this? Is it possible? So TLDR is that it seems perhaps, but probably not for the visually not very obvious case of Gaussian blow. In particular, in this stripe, which is kind of in the middle picture, you're looking at a model that learned to rely on the spurious signal. But when it was given normal input, so pictures with no stripes, it looks that the results that you're seeing is kind of sensible, which alerts us to think that, okay, maybe it really depends on the spurious correlation, and even something kind of visually obvious like stripes may not even work. So what do we learn from this? Well, to reiterate, I don't think good intentions are enough. We all had good intentions, but until 5, 6 years after a lot of these methods are invented, nobody thought to check this very basic question. And in fact, I confess, like, we didn't even set out to check this question in this very sanity check work. We actually was trying to develop a new method, and we're trying to test if there's a bug in our code. And we stumbled upon this very interesting and important phenomenon. Confirmation bias plays a role, because we thought that looking at bird boundary lines or the bird, highlighting the bird in the bird picture makes sense. So it was really hard for us to question that very intuitive results. And follow-up work suggests that there isn't going to be one thing that's best for everything. And this is obvious to this audience, but it may not be obvious, or sometimes it's hard to communicate that really explicitly to folks who are using it or from other fields. So we need to do a lot more work to answer a lot of these questions. So second, where good intentions are not enough, I argue that developing methods for us is not enough. We need to start thinking about how to equitably distribute these powerful technology called machine learning. So I'll present a work, it's now a few years old, but since we need this as a primer for the next session, where I'll show you how we follow this line of work to improve it over and over again in the course of many years. So again, our focus is post-training interpretability methods. So think about the saliency map that we just discussed. How is this answering the question of why was this Junko bird? Well, it's saying, okay, the pixel number 108 is this number, pixel number this is that, this is that. Well, that's a little bit unnatural, because I don't know about you, but I don't think in pixels. And last time I checked, we live in an analog world where things are not discrete. So how do we really want to, what else can we use instead of pixels to generate explanation? To help us think what else, let's think about a likely non-machine learning expert's user case. So suppose you're an owner of a restaurant and you heard about this machine learning hype. So you thought, I'd maybe give it a shot. So you bought some models, you trained this model to predict what pizza is going to be popular this summer. And in that model, it came with the saliency map, and you start squinting at this particular picture taken by your customer. And as you look at it, you notice, oh, okay, there's some tomatoes are highlighted in this picture. The crust, sure, yeah, crust is the core of pizza. But also the wine behind the pizza picture, which kind of makes sense. I mean, beverage is very important in that goes well with the great pizza. So you wonder, okay, is this true in this one pizza picture, or is it true globally? So that should I do something about getting maybe higher quality tomato? So what I really want is have a quantitative measure of how important these were for predicting popular pizza, so that I can make a business decision and prioritize my items that I need to buy. So this work called testing with concept activation vectors is attempt to offer that exact thing, quantitative explanation of how much concept was important for prediction, even if that concept was not part of the initial training. So how does this work? I'll explain using a zebra example. You have a zebra classifier, zebra or not, and you're curious how important the stripedness concept was. So how do we define concepts? We do a simplest possible thing. We define that as a vector, and we call that concept activation vector, or a CAV. To learn CAV, you need some examples of that concept that you identified as an interest, and you need access to the network and their internal tensors. And then what you do is you gather all the activations of the concept and gather all the activations of the random pictures, train a linear classifier to separate them, then get the vector orthogonal to the decision boundary, and that's CAV. This is not a new idea. There has been many works that show that this linear vector that represents semantically meaningful thing exists in the activation layers. So cool, you have this vector. What do you do with this? How do you get that number, the TCAV score? It's also pretty simple. Instead of getting the derivative of the pixel, we're going to take a derivative with respect to this vector that we just got. So what this does is I'm going to test the sensitivity of the probability of a zebra as I move along this vector, And at the end of the day, you get a TCAV score that always is between 0 and 1. That represents what's the ratio of the zebra pictures that I got where directional derivative were positive. What does that mean? It just means that how many pictures, ratio of pictures that existence of stripedness increased the probability of zebra. A pretty simple idea, but you should probably have a lot of questions about this. Okay, so that's cool, but this vector thing you talked about, it's pretty high dimensional space. We know the funky things can happen. Is this legit? I'll show you one way, and I'll show you later another work that's not mine that came out to further improve this point. So first, the thing that we suggest to do in our original paper is that, okay, you get, instead of one CAV, you get many CAVs using many different sets of random images. And then you pretend that these are samples of this distribution of TCAV scores. So now you have a bunch of TCAV scores for the same target zebra. And you do statistical testing to ensure that that distribution is statistically significantly different from TCAV score from random CAVs. So random CAVs are where everything is random, and random. And you should only use the ones that pass this test. So we had some results in the paper using some ground truth data and some medical application. But I'm happy to share that a couple of papers that use this TCAV in the real world problem. And so this is work from King's College London, where they trained a model, joint trained a model of VAE and a classification model to classify a coronary artery disease, CAD. And what they did, because they also had a VAE, they were able to generate images of a particular concept by moving along this CAV, which is really cool. And the part that was really exciting to me is in their conclusion, they wrote, interpretability using known biomarkers allows the model's prediction to be placed in the context of current medical knowledge and clinical decision-making guidelines. And I was thrilled when I read this, because this is exactly why we invented TCAV. We wanted to use the language of the users, whether that's a doctor or a restaurant owner, to put that in their context, in their domain knowledge, and in the domain that they're familiar with, so that it could be powerful and they don't have to speak language of computers to understand machine learning. Here's another great work came out of the DeepMind. This is extending TCAV for RNNs. I love the way that they explored many different ways to define a concept vectors along this time sequence. They tested with ground truth data to figure out which vector is better in what cases, and finally testing with the real world data set, acute kidney injury data set. There's been many other examples in radiology, radiomics, and breast cancer as well. And here's another favorite example of mine, where Eric's work on explaining a model that predicts category of storm, and concept images involved eyes of the storm. And I met Eric actually at a conference where he taught me this important lesson that choosing the negative images when you train the CAV to be similar to the original, to the satellite images, which is like black and white image, was really important to make this work in his case. Here's some work, follow-up on fairness, Google fairness, and also worked on text data for the language model. And here's work that I recently encountered, published this year at iClear, that can debias a concept. So if you might have this question about, okay, well, stripedness concept, what if you only have a striped t-shirt in your stripedness concept? Then you have this confounding factor of t-shirt concept inside of your striped concept. And they, in this work, propose a very elegant instrumental variable-based methods to debias the concepts. Here's another work that, along with many other really interesting results in this paper, one that caught my eye is you can debug GAN with these concepts to some extent, like removing this neuron improves the quality of generating kitchen examples, or by removing like the window neuron, for example. I was really thrilled to see responsive from outside of academia. After all, this work was trying to reach the folks typically outside of the machine learning research community. I was really excited to see Sundar giving a brief of how TCAV works at his keynote in 19, and UNESCO awarding this work as one of the NetEx Expro award in 19 as well. So lastly, one progress is not enough. Keep asking how to make them better. I know we're a little short on time. I'll try to go quickly. If you have questions and we don't have time for Q&A, happy to answer any questions you may have through emails or other venues. All right, so we did this TCAV work a few years ago, and it's like, okay, that's cool, but what if you don't have concepts? What if you don't know what concepts to start with? Can we automate that concept generation process? This is work with Amirata for New York's 19, where we assume, okay, you don't have these concepts examples, then what do? The one way, this is like simple method, and I love where simple method it ends up being the most effective one and not the like bells and whistles method. This is a simple method. We first took an image and used off-the-shelf superpixel methods to segment these images many times and discover these patches, what we call image patches. We cluster them using activations, and we evaluate them using the TCAV score metric. Now, one of the most important part of this work is validating that what we discovered is in fact meaningful. So we did first test to see if users can tell one odd one among this set of discovered concepts, and the answer was yes. And second human subject experiment, we asked them to name the concept in addition to other tasks. And it turns out that more than half of people put the same English word in our discovered concept. And if you count the top two of them, in fact, 77% actually named the concept in the same terms. And this highlights how it is very consistent enough for that many people who've never met each other were able to put the same name for this discovered concepts, at least for this data set. We did the quantitative testing. We add and remove according to the importance patches that we discover, and accuracy follow the right pattern. And this shows that discovered concepts are not just interpretable, but are important for the model, that these are function of, it plays a role in the prediction. It's part of the function. Some qualitative results. You look at this Jinli Kisha class, where it was able to discover this very jagged boundary that carves out humans and pointing out that as most salient. But when do you stop? Sure, you can automatically discover as many of the concepts you want, but when do we know that things are enough? This is work with Chikwan, where we defined a way of completeness. And the motivation for this was to mimic the way that PCA is formulated, so that under simple assumptions, the metric of completeness, our completeness, is equivalent to top K PCA vectors. And we approach it in a similar way. We decompose the activation into concept vectors. And we show that, yes, our green line is ours. That is comforting to see that line. And also really nice to see that ACE work, the one that I just presented, also monotonically increasing the completeness as we add more number of concepts, which is comforting. Oh, and by the way, this work discovers concepts across classes and not just one class at a time, which is what ACE was doing. So that's cool, but you already have these labels of concepts in some cases. So in those cases, can we just build a model that explicitly models those concepts as a neuron in a bottleneck? Sure, we did that. This is work with Pang Wei and other folks in Stanford. We say, okay, but remember, you only need concept labels at training time. You don't need this at test time. First, we checked, okay, are we sacrificing the performance? The answer was no. We actually can improve just slightly or equivalent to model without this explicit bottleneck. And bonus is that we can interact and control with this model. For example, if you don't think trees are important for the zebra, cross it out at the prediction time for a prop and you have the zebra prediction. This is particularly useful, as you can imagine, in medical settings where doctors don't think that this symptom should influence the diagnosis. And we did exactly this with the arthritis data set, and we show the improvement of the performance. What about, so for the interest of time, I'm going to skip this causality part. We made it causal, and we build generative models to generate that alternate universe counterfactual, and we show that, yes, you can also do this in a simple framework. More recent work that I would like to highlight is that, we so far only looked at global explanations. You can explain all the zebra pictures, but what about my zebra? I have these 3 zebra pictures. Some are taken from far away, some are from zoomed in. What about this specific local explanation? This is work with Jessica and Sebastian from Google Health and DeepMind. This is to combine TCAV with integrated gradient. And in short, the method uses concept vector as a path to integrate over instead of different images, which is what IG does. And one can view this as a projection of a particular path of IG. And of course, the baselines are important and tricky part of IG. So we propose a few new baselines for concepts like concept occluding or forgetting. And here's my favorite examples. This zebra picture, zebra far away. When you look at zebra from far away, it kind of looks like horse. So horse concept is scoring high, but decrease as you go zoom into the zebra picture. Here's a basketball where, jersey, the clothing that the player is wearing becomes more evident in this picture from moving from B to C to D, and that's well reflected here. Floor is more prominent in the first picture, and that is also reflected in this figure. These are cherry-picked examples, of course. You can look at also the quantitative metrics and subject experiments in the paper, which are coming. I think it's on arXiv. So I hope I convinced you that good intentions are not enough, and we need to do our diligence to test, think about users, and keep improving. And super quickly, I'd like to learn my lessons learned from working with product teams at Google, where I learned research is really not enough. Just doing research is not enough. People love convenient tools, and they often ended up using whatever that's easiest for them. But we have to hold them high standards, especially if they're working on high-stake domains. Often my goal has been helping them distrust the model rather than helping them trust the model. That often are proven to be more important than the other way around. Papers just themselves are not enough. The users always have different needs, different caveats, different things to worry about. And it's important to tell them, not focusing on telling them what they want to hear. And of course, this audience knows really well about how the machine learning community ourselves can't really solve this problem alone. Safety, interpretability, we need lots of expertise to really get a good step at this problem. With that, if we have time, we'd love to take questions. If not, thanks for your attention.
Thank you very much for this very interesting and inspiring talk. So we still have time for 1 or 2 questions. Do we have questions in the audience? You can open your mic and directly ask them.
don't bite. You can ask questions, relevant or irrelevant.
Okay, then I'm asking a question. So what comes next from your research? So what can we expect for CVPR 2020 from you?
That's a great question. I'm working on a few really interesting work. I'm working with DeepMind to interpret AlphaZero. AlphaZero is a self-trained chess player machine. And that's been super interesting because this is a machine potentially had no input from humans, and it just learned how to play chess by itself. So what kind of concepts or other things that it learned, how do we make sure that we don't try to shoe in that model into our perception? So that's one thing. I'm also working a lot in science. Now I'm working with neuroscientists in CMU and UIUC to see if interpretability can help science to discover new things that neural network or models had learned that humans didn't know before. And that's been really humbling experience, learning so much about this different field that's incredibly important.
Okay, then we are looking forward to next year, CVPR. Are there any more questions?
Yeah, actually, I think I have a question, but I'm not sure if I have it fully formulated. Thank you very much for the talk. So I was wondering, you explain the outputs of the models in terms of the concepts that are activated, right? And these are in some of the models, these are nonlinear embeddings of the patches themselves. So in a way, isn't this also like just pushing the problem? Like it's of course like a good step in the right direction, but isn't this also pushing the problem towards classifying these concepts, and then you don't know how the embedding model arrived at this representation?
Interesting. So there are two interesting questions that I see. So one is, are we showing in this model again to what we can understand? And versus, isn't there? And another question is isn't there a distinction between how the embeddings arrive at what it is that supposedly represent this concept? And it only tells you where it is in a way, and it doesn't tell you how.
Yes, exactly. And you don't also know, as far as I understand, whether this actually the concept was found, or if this was an out of distribution patch that was similarly embedded, right?
Oh, interesting. Yeah, those are really interesting questions. So first, to answer your first question, yes, I think the work of automatically discovering concepts, while it's not perfectly solve that problem that you're commenting, it is trying to give the voice to the model. So instead of shooing you into my model, can you tell me what concept you learned? It's not perfect. It can have that confounding factors too. But another thing I should mention is to guide ourselves from arbitrarily deciding that this concept matters, that concept matters. We do that statistical testing that we briefly mentioned to make sure that what we're looking at has that global support all across in the embedding. Your second question is super interesting. I don't know how did the embedding arrived at the information, and for example, can we attribute that back to a training data set that it had seen before? That's an interesting question, and this method does not answer that question. It's really interesting thing to investigate too. Did I answer your question? I know there's
yeah, no, that was a very I got the answer. Thank you very much.
Thank you. And I see another question in the chat. I'll read it. What do TCAV scores look like if there are unseen weird combinations of concepts? For example, a blue zebra with uncommon background. Do you mean that concept had this weird combination of the concepts, or the class had this weirdness in it? So if the concept is showing a distribution of pictures that the model has never seen, so blue zebra, then my guess is that it will not pass that statistical testing, because from model's perspective, you train me with black and white images and now you're showing me colorful pictures. I have no idea what this is. So the statistical testing of separating from the TCAV concept-based TCAV scores from random TCAV scores hopefully would not pass that test. If you meant that the target class there's some mismatch between the concept images and the target images, I project that a similar thing would happen, that it wouldn't pass the test. But if the two classes still share a shape of a zebra, for example, the colors are all over the place, but shape of a zebra, and suppose that your model actually looked at the shape of a zebra and not just a pattern, then I suspect that aspect might still pop up. And this is a case of a confounding potentially that I mentioned, that if your concept in this case learned both blue and zebra shape, and the blue doesn't matter, but your concept picture had only blue zebras, then you're kind of doomed, right? And that's when you want to use this method developed by folks in Amazon that was in my slides to debias them using instrumental variable.
Okay, thank you very much. I think we need